All right, we're finishing, we're in 6-1. We'll do 6-3, 6-5, 6-6 is the order. So here we go. This is where we finished the other night, determining whether things were exponential growth, decay, or neither. Note that the base here is above 1, and it has a positive x. This base down here is also above 1, but look at the exponent. It's a negative x, which means decay. And of course, this one, the variable is down in the base part of it, and it has to be up in the exponent for it to be an exponential, because that's what we were, all the criteria that we were looking at the other night. Now, let's do some evaluating. If f(x) equals 7 times 5 raised to the x, what's f negative 4? So it's really 7 times 5 raised to the negative 4, right? So if you evaluate that, just a regular chug and plug, right? You'll get I got that out to 4, right? Y'all agree? Everybody in agreement? 7 times 5 raised to negative 4, right? Okay. That negative 4 is really like that 5 being to a 1/5, right? Okay. 1/5 raised to the 4th there. All right. Population in a certain region has an annual growth rate of 7% per year. In the year 2012, there were 24,800 foxes counted in the area. What is the fox population predicted to be in the year 2021? Round to the nearest fox, right? All right. So we've got to make sure we understand that we've got to come up with an equation that looks like this, right? Y equals A times B raised to the T. Well, B, because this is a growth, right? It's 1 plus R, and this happens to be the R. So that's 1 plus 0.7, which is 1.0 what? 7. That would take what they have plus a 7% increase, right? Now, what you have to understand is in 2012, they told us there was 24,800 foxes. We said earlier that this A is an initial value, right? Correct? So what we have to understand is we're going to say T equals 0 at 2012, right? So 2013 would be 1, 2014 would be 2, 2015 would be 3, so forth and so on, right? We're not going to be entering 2021 as an X value. It's just not going to happen. We're going to reset the clock, and because we have to have an initial value, right? And since they told us at 2012 there were that many foxes, we can say, okay, starting now, going forward. So what we have is this. We have Y equals 24,800 foxes, right, times 1.07 raised to the T. Now that T, guys, is going to be 2021 minus 2012, which is what? 9. So I'm going to replace T with 9, right? So let's figure out how many foxes we have. Evaluate that. I got this. Well, it said round to the nearest fox, right? So that would have been what? Yeah. Right? Yes. In 2012, the population is 24,800. So they gave you initial value. Yeah. We had to have that initial value for the A. And they have a tendency to do that with word problems. 2013 would be one, right? Right. Yeah, anything raised to zero power would be 1. 24, 8. Yeah, yeah, yeah. No, not a problem. That's a base to an exponential. If we look back over here, somewhere over in here, one of these things that I think they told us. Maybe they didn't. Maybe they just assumed. Nope, not there. Nope, not there. Not there. Not there. Nor there. Okay. All right. So um, you have B. If it's growth, it's 1 plus R. If it's all right, decay. Boy, that's wicked drawing right there. So it's 1 minus R if it's a decay. Like if it's decreasing by 10%, then that would be 1 minus 0.1, which would be 0.9. It's kind of like discounts. It's 30% off, you still got 70% value there, and that's what your base would be. Yeah. No, the RS. The RS, yeah.
Where does the 1?
100%. The 1 is 100%. It's what you got plus that much, or what you got minus that, right?
Okay.
So that's what the 1. The 1 is equaling 100%, right? Because the R is being put in as a decimal, correct? So that's where the 1 is. Yeah. All right. If we were really doing this, there would only be 45,593 foxes, technically, right? If we were physically counting them, because that 0.789 would mean that there's a fox that's pregnant. Okay. Huh? No, it didn't chew off a leg. It's doesn't chew off a leg. No, no. It's a portion of a unborn fox. So there. And it's 3/4 of the way through, so there, it's in its last trimester or whatnot. So there. So a little bit of time left, okay? All right. So let's look at this one. For each year T in the population of a forest of trees, call it forest A, is represented by the function A of T equals 103 times 1.025. In a neighboring forest, call it forest B, the population of the same type of tree is represented by the function B sub T equals 83 times 1.029 raised to the T. Which forest population is growing at a faster rate? Well, forest A has a rate of 1.025 and forest B has it 1.029, right? Really, that's 2.9% and 2.5%. Are y'all tracking when I say 2.5%, 2.9? If I were to go, that's my base. If I had a minus 1 off of them, that would leave me the decimal part of the rate, correct? So that's the same as saying 2.5% or 2.9%. So really it would be what? Forest B. Which forest had a greater number of trees initially? Well, we said that the initial amount was the number in front of the base, right? So 103 and then 83. So that would be forest what? A. By how many? Well, 103 minus 83 would be what? 20? By 20 trees. Okay. Are y'all okay with that? Everybody tracking? Good? No? All right. Assuming that the population growth model continues to represent the growth of the forest, which forest will have a greater number of trees after 100 years. Well, what are we going to do with 100? Put in for T and evaluate it, right? Yeah. So let's put it in for T and evaluate it. Route to the nearest tree. So not even close. Well, there you go. So who's got it? Forest B by how many? 14. I got 1447 minus 1217, right? Y'all agreeing with me? I got 1260. 1216.81 round to the nearest tree, right? So if I use rounding, it would round what? Up, right? 5 and up go up. Below 5 goes down, right?
Population thing, don't you? Because you can't just round up and say you have a whole of something.
Well, you can if they tell you. Yeah. It. Yeah. Just use rounding principles. Yeah. Don't worry about it. Yeah. It's just a seedling that hadn't broke through the ground. I can split hairs on that. I mean, you got to wait 6 tries to get it right, correct? So put in, what's it, 1447, let's see, minus 12. So 230, right? So if it doesn't like that, what? 229, 231, right? Whatever you want to do, it'll be all right. So, all right. Any questions on that? Y'all good? Okay. Now, here's the fun part. We're going to write exponential equations from 2 points. Now, you've probably been exposed doing this when you did geometric sequences, okay, like missing terms in a sequence. But I want to show you something. This is pretty cool. So we're trying to write y equals a times b raised to t, right? Correct? So let's kind of look at this. You always put the biggest one on top, right? So what's what I'm about to do? Y, this is x, there's y, right? So 16 equals a times b raised to the third. Then I'll do this one, right? 2 equals a times b raised to 0, right? Y'all with me? I just substituted input and output, correct? Okay, now, this is cool. Let's subtract them. Well, I say subtract them. Let's divide them. We're going to subtract their exponents, but let's divide them. What's 16 divided by 2? Yeah. Now, what is anything over itself? 1. Thank you. So the A's go away, right? A's go away. So, wait, there. So what is 3 minus 0? 3, right? So it has a number equal to b cubed, right? Some base cube. So how you get rid of something cubed? You take the cube root, and ladies and gentlemen, b equals what? 2. Okay. Now, we need to find a, right? A is when x equals 0, right? It's the y, well, A equals the y value when x equals 0. It's the initial value, right? The zero term is what they say. So if we have that, that's great. We can go ahead and put it in, right? 2 right? 2 is the initial value because if x equals 0, then A equals y, right? So there. All right, and so we already found the base, right? How many of y'all have ever wrote equations like that before? It's pretty slick. There's much harder ways to do it if you'd like to try. No? There you go. Yep. 2 is the initial value. We found that the base happened to be 2, right? So 2 times 2 raised to the x. And if you want to check it, then plug 3 in there, right? 2 raised to the third power is 8. 8 times 2 is what? 16, right? So there, it gives us, right? All right, so you got that? Well, I gave you another one, right? Because I wanted you to try it. So go. I'm going to hit pause. I'm going to give you about a minute, and then I'll pick up. All right. So when I substituted everything in, I got 243 equals a times b to the 8th. And then the other coordinate I substituted in was 3 equals a times b raised to the 4th. 243 divided by 3 is 81, right? So 8 minus 4, I've done the quotient property of exponents up there, gave me b to the 4th. And to get rid of b to the 4th, I took the 4th root. So the 4th root of 81 is 3. So we know what our base is, right? Now, here's the kicker. The easiest thing is to do this. And it falls back on geometric sequences, okay? So I'm going to take you down a path that you may or may not have ever been. All right. So if we know that multiplying, going up on outputs, that it'd be multiplied by 3, then if we go backwards, then it should be divided by what? 3. So if I divide by 3, that'd be 1. If I divide by 3, that'd be 1/3. If I divide again, that'd be what? 1/9. So if I divide again, that would be 1/27. Okay? It's nothing more than, think about slope in a table, right? On linear, it goes up by a constant. rate, some constant, well, I say constant rate, some constant rate of change, right? But on exponentials, there's a common multiplier, right? If you're going up the table as x increases, the constant multiplier is either going to make your numbers get bigger if it's a base above 1, or if it's a base less than 1, it'll make it get smaller, right? So, but if I want to back it up, then all I have to do is just take the outputs and keep dividing by 3, because if I go the other way, 1/27 divided by 3 is 3/27, which is 1/9. 3/9 times 3 is 1/3. 1/3 times 3 is 1. 1 times 3 is 3. 3 times 3 is 9, so forth and so on. Okay? That's what you're doing. You're manipulating the table. That's the easiest way to do it. Okay? So you have a constant multiplier. If you're going up, it's multiplying. If you're going down, you're dividing it. Okay? You okay with that? No. Well, I chose 4 because I took the 4 through, but look at this. This is x and that's a y. So the smallest x value that I have was a 4. I wouldn't want, I mean, I could have done 8. I mean, I could go all the way up 5, 6, 7, 8 and just take 243, divide by 3, divide by 3, divide by 3, divide by 3. I'd still get exactly what I got right there. Okay. So you just need to make sure that you are able to think flexible about exponentials in a table. It's a constant multiplier, right?
You got divided by 3 because your b equals 3.
Mm-hmm.
It's constant. Okay.
Yeah, if I'm going up, like I would take, what's 3 times 3? So the fifth term would be 9. 9 times 3 would 20. So 6 terms would be 27. Times 3 would be, I don't know, what's 27 times 3? Something 1, right? Yeah, something 1, right? 81? Yeah, that's 81. And then times it by 3, and it should be 243, right? Yeah. So you can do that. If you're going up, you're multiplying it by 3. If you're going back down, then you're dividing it by 3. That base, right? Yeah? Oh, sure. Here you go. So this was what I was wanting, right? The 0 term, right? What's happening in the beginning? So it's 1/27 times, base is 3 to the x, right? 1/27 times 3 raised to the x. Works every time. Okay. You normally would have to write the equation for it. In previous college algebra classes, we never had to, but this one does. So, yeah, there you go. You know how to do it now. You could do a exponential regression on it if you wanted to. It'd give you that. Well, that means you could type in these 2 ordered pairs in your stat list, and you can perform an exponential regression where you punch a number, and it will give you back the equation. Exponential takes 2 points. Linear takes 2 points, but a quadratic takes 3 to do a regression. That's crazy. All right, y'all ready? Ooh. A car was valued at $31,000 in the year 2009. By 2013, the car had depreciated to $15,000. If the car's value continues to drop by the same percentage, what will it be worth in 2019? Round to the nearest dollar. So, first off, we got to write an equation, right? I mean, it'd be helpful. A times B to the X, right? Well, we know what A is, right? Yeah, it's 31,000, right? In the beginning, the car was 31,000. Now, by 2013, it depreciated to 15,000. So what you want to do? How many years is that? How many? So 4 years. What did it depreciate by? What is its percentage that it went down? How much? No, 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 no. What percentage? Not how much. You can't give me a little 50. Come on now. Okay, we want exact, okay? Okay. Okay, so we're going to write this, all right? Let me give you another equation that's, okay. Yeah, okay. Yeah, we could get to it that way. Uh, so what? That's the fourth. Well, okay, hold up. Let's do this. Well, we'll just do what we done just a while ago. Right? Correct? Four is what? Can we write an equation that way? Yay or nay? We sure can. We made ordered pairs. It'd be just like what we done, right? It'd be a whole lot easier than a couple of other ways that was going through my head. So let's let you do this as X and Y's, right? That's exactly what we just got done doing, right? Okay, so let's let you go. Anybody lost? All right, so we done some math. We got B to be 0.34834. So we're going to write our equation now. Y equals 31,000 times 0.834 raised to some time. Now, this is time equals 0.09. 19 would be how many years? 10, right? So it would be 31,000 times 0.834 raised to the 10th. So we'd have 834 round to the nearest dollar. So that would be what? 5,047. That's what I got. How'd you get? Yeah? Okay. Any questions? Yeah.
The 0.84, that's the percent remaining.
Yep.
You go to 16% from the 0.166 would have been the decrease, right? So that's how. So I just got like.
Yeah, the 16.6% would be how it's decreasing, right? So we 1 minus that, which would leave us 0.834, right?
Okay, so each year it has 83% of its original value.
Yeah.
From, okay.
it's got 83%, 83.4% always remaining after every year, right? Yeah, that's what the base does for a decrease. We think about, it's kind of like when you're a discount, you know, that's how much money you're not paying, right? But so how much is it really worth? Well, how much value is still left there? So decreasing, you always look at what's left, and that's the 0.834. Yeah, that's about the easiest way to do it. Ties back into the previous problem. So, yeah. Okay. Let's do some compounding continuous. So, and well, it's this, right? PERT, right? Compounded continuous should be PERT, right? So, and that Y normally is an A, but let's look at it. So we've got a P as a principal, right? T is time in years. R is interest rate as a decimal, right? So that's what you got to make sure you understand. So let's go, I'm going to change that to an A. A, P, R, and T. A is what you have afterwards. So if initial investment, $1,800 at 7% interest is compounded continuous, what would the investment be in 8 years? There you go. Where? No. Oh, here. Where? Oh, that's. Oh, yeah, if I could spell interest right. R equals interest. Yeah, it's all here. I'll rewrite it. There. There you go. So if we plug this in, we get 1,800 times E raised to the 0.07 times 8, right? So E is a special exponential. It's 2.71828 da 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 da. It's never ends and never repeats. It's a constant that was discovered by Euler, E-U-L-E-R, back in the 1700s. And it's just been really used throughout all exponentials. Uh, 2.71828 dot 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 dot, right? So it's just a base that things are growing or decaying by naturally. Okay, so there's a constant that kept on showing up all the time. And what they done was he named it E. Probably after himself. Yeah. So if we take this 1,800 times, there's E. E is right, should be above your LN button. LN's natural log. I know it should be NL for natural log, but it's LN. So if you go back in a time machine, get them to change it, okay? Huh? Uh, all right. So after 8 years, this joker ought to be at that amount, right? $3,151.21. Is that good? Yay or nay? Yeah. 8 years, $1,800 now. It didn't even double, did it? Huh. Okay. Any questions? You good? Huh? Um, second LN. Yeah, you got to do it's in your LN button. You got to go to E. Make sure you put a parentheses if it's not up in the exponent, written up in the exponent. Make sure the 0.07 times 8 is in all kind of in parentheses. Okay. Right here. Right here. E and 10 for you, this one. For the TI-36X Pro, it's the third button down on the left. E, power of E, and then 10. But it'll keep it up there. Yeah. Is the multi-views there? Does it have a 10 and an E button? What do those look like? Or they have an LN button? That's an LN. Above LN's the E to the X, right? Okay. All right. Okay. 1800 times E raised to the 0.07 times 8. Yeah. Yeah. Y'all good? Okay. All right. All right. $3,151.21. Everybody agree? Yep. Okay. Good. All right. So let's look at stuff that is let's look at it again. An account now contains $1,631.25 and has been accumulating 7% interest at an annual rate compounded continuously for 6 years. Find the initial deposit. Well, A equals PER. Sorry. ERT, right? So, they've given us the ending amount. They've told us what the rate is, and they've told us what the time is. They want to know how much do we start with. You go, well, I just keep punching numbers in until I get there. No, there's an easier way to do it. All right. So what are you going to do first? Can't subtract. Divide. Yeah. Divide. Because it's times P times, so so we'll just divide. You could do 0.42, right? If you wanted to. The 0.7 times 6 is 0.42, right? Yeah. So, but there. So 1631.25 divided by E, 0.7 times 6. Boom. So I got an initial value of $1,071.81. You okay on that? Y'all good? Yeah. No, ma'am. No, ma'am. We're not going to add or subtract anything because these things are tied together by multiplication. The only way to undo them is by division, right? Yeah. So one thing on the left and everything else is tied together by multiplication. So, all right. Let's look at the next one. Initial deposit of 1,100 earns 9%. Compounded monthly. All right, so this one is compounded interest, right? So compounded monthly, the N is 12, right? Okay, so we're going to set this up. We have A, P, R, T, and N. N is the number of compounds per year, right? So if it's monthly, that's how many per year? Be 12, right? We want to find out how much is earned if we put $1,100 in at 9% interest for 4.5 years. So that's 4.5 compounded 12 times per year, right? Do you understand what compounding is? Yeah or nay? Okay. So you put your money in an account, right? And it draws interest. So you think about that interest is sitting over here in another bucket, right? 12 means that that interest is going to be dumped back on that principal 12 times in a year. So at the end of the month, what interest you made now went back in that bucket. So your principal is what you had plus your interest for that month. So now it went up a little bit. Now you're making interest off that, right? And then it's going to come back in. And then you're up a little bit more, right? So it's how many times does that bucket put dumping back into that initial principal? So anybody know what the interest rate is now for any kind of loan? Well, for savings or anything like that? Anybody? It's like next to nothing. Huh? I don't think they've raised it yet. Yeah. I don't think it's happened. I mm, what is it currently? What's prime? All right. Okay. The first calculation that I'm going to do is I just plugged it in there, but I'm going to do 12 times 4.5, which gives me 54. That way I've got a power, excuse me, a power, one power instead of a product that I have to do. Now, what we're doing is taking this 9% annual interest and splitting it over 12 months, right? So I'm going to tell you how to do this a lot easier and make sure that everybody comes out with the same number every single time. You do it this way, you will come out with the correct number. You do it some other way, you're going to be off, okay? All right, you ready? All this is order of operations. On your calculator, 0.09 divided by 12. Enter. Okay? Now, so it took care of, we always work parentheses, right? So 0.09 divided by 12, enter. Plus 1, enter. Right? Now, we're going to take that and raise it to the 54th power. Enter. And you should have something that looks like this. Now, times 1100, right? And that should all get us at, if I can write this correctly to get us all at the right number, 1646.74, right? Yeah. Now, if you do it some other way, if you start rounding off or anything like that, you're going to introduce error. And you start doing it with exponentials, and error can can be dramatically affected or compounded on it. Okay, so $1,646.74 for 4.5 years. You could, but you know what happens when you try to type it all in? People don't put parentheses where they ought to. People don't, I mean, I don't know. There's no class that says, please take order of operations, right? We're going to master you on how to do it with the simplest of steps and right now. No. So I just kind of, you know, force it. I just kind of force my order of operations to happen. That way I know I've got it right. I can guarantee you after 9 years of teaching here that if you do it like this, you'll be fine. Yeah. The what now? The 74 cents. Did you do it like I done it? Are you sure? I don't believe you.
You have to take the entire number that you get.
Yeah.
You can't
I
round.
don't round. Don't round. You take and like 0.09 divided by 12, enter. Right? Now hit +1, enter. And what it'll do is it'll take that previous answer and add 1 to it, right? Hit enter. So you always should have, when you calculated this ANS, right? Which is what she was saying. If you take and you round it, you're going to introduce there. You'll be a couple pennies off. We don't want to do that. Did you get it? You got the same as I got now? Okay, good.
So you solved it inside the parentheses to multiply it times 1100.
Yeah. No. I took the 0.09 divided by 12, added 1 to it, raised to the 54th power,
Okay, you're right.
54th, and then multiply it by 1100. Really what this is, guys, and I want you to see this. Do you know what this right here really is? What is that right there really? Anybody know? Remember we talked about earlier, base equals 1 plus r, right? That's really what you're doing. You're breaking it down, right? But see, it's at 9% over 12 months or 12 compoundings, right? So you're breaking that 9% over that. That's what you're doing with the R. Okay. So, okay. All right. So suppose it takes 6 hours for a certain strain of bacteria to produce by dividing in half, to reproduce by dividing in half. Hello. Oh, okay. If 40 bacteria are present with a total present after X day is 40 times 16 raised to the X, find the total present after day 1, day 2, day 3, right? Well, what is that? That's just a regular chug and what? Plug, right? So I would have 40 times 16 raised to first, and then 40 times 16 squared, and then 40 times 16 to the third, right? Let's see. So I got 640, 10, 240, right? And then what? 163,840 after day 3. Any questions? Just a regular chug and plug, okay? All right. A golf ball is manufactured so that if it's dropped from a height A above the ground on a hard surface, the maximum height of each bounce will be 1/2 of the height of the previous bounce. Okay? Now that's pretty cool. So if you dropped it 6 foot, then the first bounce, the height would come up to what? 3, then it would come up to what? 1/2, then, yeah, of a foot, right? Yeah, that's pretty cool. Huh. Find an exponential equation that gives the height to the ball, h, that will be retained after nth bounces, right? Um, so here we go. Do we know how high the ball is? Nah, we don't know. So h equals the initial height, right? H sub 0. Are you okay with me using H sub 0? That's initial value of height, right? Times what? 1/2 raised to the what? N, right? The H sub 0 is nothing more than A. How high is it in the beginning, right? And normally they'll do sub zeros or subscripts as being initial values. So if the ball's dropped from 24 feet, so height equals 24 times 1/2 onto a hard surface, how high will it bounce on the 7th? So guys, there you go. So 24 times, you better make sure you put the 1/2 in parentheses so that you're not doing 1 divided by 2 raised to the 7th, right? I got this. .1875. So let's see. Uh, haha. 6:30 seconds. 6:30 seconds. I take .1875 as 6:30 seconds. Huh? Okay.
Oh, I did get it.
I went 16th, but no, I went straight from 8 to 30 seconds. Sorry. You're correct. Yeah. So 3/16, right? Okay. Any questions? You put the decimal. Yeah, you'll put the decimal. Um, it should have some kind of variable for you to put as the initial height. Something to be right there. Okay? Just be aware of that. If it doesn't, then let me know and I'll kill the problem.
So on the test, you see our option will.
It should have something for that. Yeah. Mhm. Yeah, but it doesn't say how many decimals. It may have said, and I just didn't paste it on there. I just normally grab the problems. I don't grab any frou-frou information. Huh? Ten thousandths, right? So it's 10 thousandths. Say it as a decimal
No, so it's gonna reach a height of 0.1875 feet.
of a foot. Yeah. So that'd be
Yeah, it's, the percent.
3/16 of a foot, right? We were going 3/16 of an inch.
Yeah.
Yeah, we were mixing up units. But 0.1875 is 3/16. Yeah. So yeah, that's yeah. All right. So let's do this one. Oh man. Suppose $1,900 in an account with an interest rate of 9% is compounded quarterly. Use the formula that's given and round each answer to 2 decimal places. We're dealing with money, should be 2, right? So find the equation that gives the amount of money into years. So we're going to plug this in, right? So P, A, R, N, and T. If you'll fill this out, then it'll be easy to plug in. So that's 1,900. Interest rate is 0.09. Quarterly is what, guys? How many times a year? 4. And then for how many years? Oh, it just said 2 years, right? So you do the equation 1,900 times 1 plus 0.09 over 4 raised to the 4t, right? And then want you to find out how many years. So it would be 1,900 times, or how much would be in the account after 7 years, right? And that's 7 times 4, which is 28, right? So we'll take that. We'll do 0.09 divided by 4 plus 1 raised to the 28th power times 1,900. Whew, I got 3542. Son, that's awful big, but yeah, 6.4, yeah. 3542.64. You agree? Yeah, regular chug and plug. And if the interest were compounded continuously, how much money would be there after 7 years? So well, that one would be A equals PERT, right? So that would be, got $1,900 E to the, right? So that would give me $3,567.46. Just a little bit more money, right? When does compounding, or when does interest really start to become a factor? Yeah, the day you put it in, you start gaining interest, right? But when do you start to make bank on interest? Mm-mm. Huh? Yeah, the more money you have in the account. The principle of 401ks, right? You know, they say start when you're young, so when you get to retirement age, you've got over $1 million in your 401k, right? Well, you start out, I mean, first couple of years, well, first 5, 6 years, I mean, depending upon how much you're putting in, and always put in what they'll match. That's a minimum, right? They match up 5%, buy grannies, put up 5%. You start to have, you'll get 20, you'll get up to 20, maybe 30,000 and stuff, and then it start getting, yeah, you get that baby above, and then it starts really hopping. But that's time, and it takes time to get there. Okay. Huh? No, just time. It's all based off time. Is it 18%? Can you do? Is it 12? Is 12 or 18% is coming to my head for some odd reason. So, but that's it. So when you get out of here and you start in your career and all this stuff, and they say, hey, retirement savings and this stuff like that, do it, and don't ever cash it out. You know, if you leave that company, they say cash it out, roll it over. If you cash out, roll it over into the next place you're coming. Don't take it out and pay something to spend money on. Mm-mm. Roll it over. Keep it going.
You'll lose almost 50% in tax.
Yeah, they'll get you to about 40% tax rate. Yeah, it's about up there. It'll get you. So there. All right. Time is your friend. Always remember that. Okay. All right. Any questions about 35, 67, 46? So we make just a little bit more money. 4 times a year is compared to continuous. So in 5 years, a father wants to accumulate $95,000 to pay for his daughter's college expenses. If he can get 11% interest compounded quarterly, how much would he have to invest to achieve his goal? It's a really good problem. APRNT, compounded quarterly. Now, we're trying to find out how much does he have to put in, right? 95,000 equals P, 1 plus 0.11 over 4. 4 times 5 is 20. Can I just go ahead and put the 20 there? I'll do it like that. 20 is 4 times 5. N times T. So what you're going to do is basically you're going to take this and move it over here, right? It's be 95,000 divided by, let's just go ahead and get what this is going to be. 0.01, sorry, 0.11 divided by 4 plus 1 raised to the 20th. So that's roughly, now I'm rounding it, so be careful. Note that you shouldn't round it, right? Keep that 1.7204 in your calculator. Type in 95,000 divided by the answer that you just had, right? And hit enter. And ladies and gentlemen, they'd have to put in $55,218.80. If he's got $55,000 to invest, what's he worried about 5 years from now? That's why they keep printing it, right? You can never have enough money to keep printing more, right? There you go. Yeah. I don't know. Not sure all my degrees even equate to be 55,000. Be close. That's 4 degrees. Yeah, I'm thrifty. Very cheap. Very. I like that. I spend money on good things instead of odd things. Okay. Y'all good? Any questions about that? Yeah, we're going to skip this bank one, and we're going to go to this one. The bank one's pretty self-explanatory, but I want you to look at this one. 45,000 gross at an annual interest rate of 11% for 35 years. Compare, right? So APRNT, annual. Well, okay, you'll see something here in a minute. So really, for annually, it would be, well, let me back it up. Use stuff that we're doing. It will tie it in. So we'll go 45,000 times 1 plus 0.11 over 1 to the 35 times 1, right? Which all breaks down into just 1 plus that, which is 1.11 raised to 35 times 45,000, right? Y'all see what I'm doing here? I'm using the compounding formula, right? But 0.11 divided by 1 is nothing more than 0.11. So 1 plus 0.11 is 1.11. 100% is 1 plus 11% growth raised to 35. So it's really the A times B raised to the T, right? But I don't, if I just wrote 45,000 times 1.1 raised to 35, you won't see how that kind of progresses through. So it's a little bit easier to see this. I know it's a little bit more work to do, but it ties back into what we were doing. Okay. Look at this. Is this yours? Okay. All right. So I need a total for that. Then continuous is just what? Let's see. That would be 45,000 e to the 0.11 times 35, right? So I'll need two totals. Let's see who makes the most money. Which way? Yeah, a little over 2 million. So there's what, 400,000 difference, a little less than 400,000 difference between them, right? 1.7, 2.1, roughly, right? If you can find a bank giving continuous interest, let me know. We will all retire early, making lots of money off the interest. So we'll crowdfund it. There. The left one is the premises behind your 401k, guys. If you want to really think about it, 5-6 years, you ought to have about, I don't know, $20,000-$30,000. Should. So 11%. If you look at historic values, that's a little high, but 8 to 9 is really about yeah. The later 2000s up to 8, 9, 10, 11, 12 when we had the recession killed us. So people lost a lot of funny money. So okay, so that's 6-1 done, right? Okay. Spoon. 6-2. Here we go. No, 6-3. Sorry. Logs. Now, let's talk about inverse functions. Okay. Inverse function. If it's a true inverse, the x and the y's switch places, right? If it's algebraically a true inverse, that's what happens, right? So an exponential, basic exponential, will go through 0, 1 on the y-axis, right? A logarithm or a log will go through 1, 0, right? So they're inverses of one another. It's kind of like multiplication, division, addition, and subtraction. Exponentials and logs are inverse functions of one another. Okay. I'm not going to put this on video, but you've got to understand that just better, because you need to see this. It gives me an opportunity to play with the calculator, right? Which is cool. So, all right. So let's do this. Clear, clear. Let's just do a log. All right. So it's kind of like I just put a common log, which is a log with a base of 10 of just x, right? So what you have to understand is, like on an exponential, the x-axis acted like an asymptote, right? For a log, now it's the y-axis. Okay, so for a generic log, and this is just a log of x, right? Y equals log of x. That's the equation that we graphed. So it will not cross the y-axis. So you can't take the log of a negative number, okay? So when you're solving logs, and we'll try to get into that, you got to make sure that you're not taking the log of a negative number because it doesn't exist. There's no solution for it, right? Because here's your asymptote here, and it's continually going down. Even though it looks like it stops right here, it's really going down. So, so that would be increasing if you have a log that has a base that is between 0 and 1, then it would be down like this, right? I can draw that on there. It would be like this. Whoa. Dude. Yeah, let's go. Which one? Let's go there. Will it go? Dang it, it won't go. Well, it ain't gonna let me write on it, but it should come down like this. Okay. All right. So let's go back to 6.3. So logs. You know why we got logs? Anybody know why we have logs? Exponentials, you evaluate stuff, get big stuff, right? Logs allow you to take big stuff and get it back down lower. Anybody dealt with log paper? Like logarithmic paper? You can graph all the way out to from 0 to a million if you want to, using log because it's scaled up and stuff. Log allows you to take huge numbers and get a small value, right? And exponentials take small numbers and get big, right? Huh? Ah, yeah, it's very much like sine. I mean, but the inverse is one another, right? So, you know you dealt with logs all the time, right? You're dealing with logs right now. Did you know that? Sound, decibel, is based upon logs. It's 10 times the log of an intensity, I sub 0, right? Sound intensity. And if you take the log, 10 times log of that, then you're dealing with a decibel. So that's what sound is measured in, is logs. What's the country that 2 days ago had their earthquake out in Indonesia? Earthquakes are measured in Richter scale, right? It's the log of some intensity, right? Equals the Richter scale. So if they tell you that you have a Richter scale of 9, and that was pretty close, right? So, okay, 7.5. You take 10 raised to 7.5, hit enter, that'll tell you how much intensity it was, how much energy was at the moment of the earthquake. So logs deal with earthquakes, logs deal with sound, and a couple other stuff, but primarily that. So, but we're gonna look at logs, and we're gonna do some stuff, and it's red log base b of x, right? This little part right here is read as log base b of x, right? So, and that's equivalent to by of x. I told you logs and exponentials were the same thing, but or I shouldn't say same thing. Inverses of one another. So I'm going to show you something real quick, and it's called the backwards C. All right. So if I take log base b of x and say it's equal to y, if I do a backwards C, because the log of a base and the base of the exponential are all the same. Okay? The base of the log and the base of the exponential are the same numbers, right? Okay, so log base b, right, of x equals y. So the exponential would be b raised to the y equals what? X. Now, if you want to take it in exponential and go back the other way, it'd be log base b of x equal to y. You'd pick up the equal on the opposite, on the top side, right? Here and then here, and you'll be able to go between forms. Pick up the equal on the top side. Works every time. The base of this log is the base of the exponential, right? B raised to the y equals who? Aha. So if I've got b raised to the y equals x, then I can say, oh, this base is the same as the log, but right? So I'd write log base b of x equal to y. Okay. All right. So we know what it looks like. We kind of look at some basic stuff between them. Let's go see what else we can find. Common log is nothing more than a log with no base, right? It's understood to have a base of 10. So if you see a log with no base, it's called a common log. Your calculator is set up on a common log, okay? Now, what the heck is a natural log? A lot of people have a lot of hard problems with this. A natural log is nothing more than a log to a base e. Okay? This right here is this. Log base e is the same as saying natural log, right? So if you ever have to convert a natural log over to an exponential, if you'll rewrite the ln as log base e and then convert it, be a simple piece of cake. Okay? That kind of keeps it clean. All right. Let's see what else we got to know. All right, it says rewrite the equation in exponential form. So here we go, guys. Backwards C. Let's see what you can do. Give you, I don't know, 15 seconds. There was a lot of theory in that problem that we just had, or the properties that we just had that we'll go back and do. So I'm going to give you, I don't know, 15, 20 seconds. All right, so we said the base of the log is the base of the exponential, right? There you go. How do we do? Yeah, backwards C works pretty slick. Most people want you to remember the switch and all. Nah, don't do that. That's crazy. They tell you that just because they don't understand what it takes to get to the back the other way, right? Okay, so rewrite this one. So let's see if you can get this one. All right, the key to this is just rewriting it as a log base e of n equals m. If you do that, guys, it becomes a piece of cake. There you go. Oh, what now? I took this and replaced that, right? Yeah. And that way it's easier. you see it that it's E, right? You understand why the natural log and E come about, right? So E raised to the M equals N. Any questions? Anybody? Good? I know you saturated, so let's continue going. All right, rewrite this in log, right? That, right? Base of the exponential is the base of the log, so that's what you ought to get. Log base 2 of B equals A. Any questions? Y'all okay on that? Okay. How about this one? Remember I said the base of the exponential is really the base of the log? And if you do that, then you should know that log base E is nothing more than ln, right? ln of x equals y. Okay. So that's how you do it. That's the key to it. Find the value of x. All right, so I'm going to show you two ways to do this. And so we'll change it back into an exponential, right? Okay. And there's a property in exponentials that's really in 6-6 that we'll see it. 6-5 is changing forms of exponential. 6-6 is where you'll really pick this up. But it says if your bases are the same, then you can set their exponents equal to one another, right? So, and I said you could work it two ways. So can I rewrite 625 as a power of 5? 4? Is it 5 to the 4th? So if I rewrote that, that'd be 5 to the 4th equals 5 to the x. So x equals what? 4, right? Now, you can also do what is called change of base. All right? So you're taking the log of the top one divided by the log of the base equals x. So what this would equal out to is here. We would do the log of 625 over the log of 5. And that should give us, if you do that, because it's common logs, right? So you do a log of 625, make sure you close parentheses, divided by the log of 5. And the base is always going to be on the bottom, right? And you get 4. Okay, you get 4. So you can do that two ways. It doesn't really matter how you do it, but there. So you can either get the exponentials to get back to the same base, or, excuse me, you can just rewrite it as change of base, right? And solve it. Any questions? You good? All right, simplify the following expression. Natural log of e raised to the 8. So, all right. There's a property that says natural log of e raised to the x is just x, right? Okay. There's also a property that says, okay, this is really log base e of e to the 8, right? When you have the base and the of being the same thing as just the exponent, right? Okay. Um, so that's just 8. Really, this property right here would probably be beneficial. Natural log cancel out an e, so you're left with just the power. Okay. So, and those properties are on the back of that formula sheet. All right, so the log of 100,000 should just be what? 5, right? Because that's a base 10, right? But you could do, and you calculate, you could put log of 100,000, hit enter, and it will give you 5, right? All day long. Because it's a common log because there's no base, correct? Yeah. So it's just a straight chug and plug, simplify it. Because it's set up on a power of 10, and how many zeros are there, right? There's 5 for this one. All right. Solve this one. Well, you've got 2 ways to do it, right? You can do change a base, or you can rewrite it as an exponential and try to get the bases to be the same, right? Doesn't matter to me which one you want to do. I don't know. I'll give you a minute to choose, and I'll work both of them. Is it 3? No, it should be something different. No, it'd be something different. Sorry. 2/3? 1? I don't know. Well, I'm sitting there guessing. Let's just do log of 9. Close parentheses divided by log of what? 27? Geez, 2/3. Yeah. 0.667, right? Now, that's change base. But if I'd done this, it'd be 27 raised to the x equals 9, right? Now, I could rewrite that as 3x equals 3 squared, right? So I could rewrite 27 as 3 raised to the power of 3, and power to a power, that's just 3 times x, right? So that's 3x equals 2 divided by 3, so x equals 2/3, right? There you go. Either way is fine. The one on the right would probably benefit you if you're going on to pre-calc or whatnot. Anybody taking 1113 in here? If you are, that's you want to hang your hat more on the right. Find the exact value of x, or find the value of x, answer exactly. Um, can you take the log of something and be negative? No, I said you couldn't take the log of a negative number, could I? When you get done taking the log of something, can you get a negative number? Well, it's an output, right? Right? Um, so, Lord have mercy, how are we going to do this? Well, here, guys. 3 raised to negative 4 equals what? Yeah. 1 over 181, right? Right? Correct. It's a negative exponent, right? So that would flip it down. Yeah, yeah. Um, You couldn't do change base on this, could you? Because you don't have the of, right? You have the base, but you don't have the of. The of's what is it, right? So change over to an exponent or exponential form. It allows you to solve it. So 3 to the negative 4 equals x. So 3 to the negative 4 is 1/8. Or not 1/8, 1/81st. All right, 1 over 81. All right. How about this one? Use calculator to find the exact value 4 decimal places. What's the base here? Yeah, so what do I need to do? 10 raised to 0.331 equals who? Yeah. How do you solve a log? Change it over into an exponential, right? If you can't do a change of base. So that would be 10 raised to the 0.331. So that's 2.1429. Questions? Make sure you think about what I'm talking about. Okay, don't glaze over here. You good? Okay. Use calculator to find the exact value to 4. Oh, snap. Well, how are we going to do that? Well, can you find the log base 2? Yeah. Look, all you got to do is say that's log of e, right? Of x equal to log of what? 2, right? It's common log, right? And I can't do change of base because I got natural log, which got a base e, and that's not base 10. So I could change it which way? E to the log of 2 is equal to x. Let's see. There's property I know that's got that. So no, you just evaluate it. 1.3512, right? Here's your go between. Natural log, rewrite it as a log base what? E. Yeah, that's the way to do it. Okay. If you don't, you won't get it. Can you take, can a log be in the power? Yeah, sure can. So. Go ahead and put to 1.3512. So that way you know what it comes out to be. Yeah, when you go back looking at your notes, you'll be able to see it. All right, y'all ready? Oh, man. How are we going to do this one? Pray? Pray real hard for a solution, right?
Log base 5, 2, however you say it, out.
Yeah, you can. And the thing about this, we haven't talked about property. We really ought to have done properties first, then logs. Because the only easy way to do this is take this. No, can't. Can't do that. Because that'd be a power to a log. That's 2. Let's go to 2. Well,
Is that saying the log of 5 to the second? Is that what that's saying?
yeah, that's what it's saying. Log base 5 of 2. All right, so let's just do this. Yeah, but hold up. Evaluate log of 5 base 2. That would give us, well, let's change base. Log of 2 over log of 5, right? Right? So the x, let's see. There's probably an easier way to do it, but my brain ain't seeing that, so. So how you get rid of something raised to the 0.4307? Raise it to the, right? If that was x squared, we'd take square root, right? How? I got log, okay, so I evaluated log base 5 of 2 to got 4.4307, right? So the x is raised to 0.4307 now, right? Right? Okay, so if it's raised to a 0.4307 power, how do you get rid of a 0.4307? And I'm going to go into 4 decimal places, right? So I'm introducing error. But I'm going to take that root of it, right? So 0.4307 of 2, and you get 4.996, which is probably 5. So if I done, huh? Yeah, so, yeah, 9, yeah. So I want to see something real quick before we go. I know y'all about ready to go. Yeah, it's 5.
Explain to me why you have a 2 over log of 5.
It's change of base. What do you mean where they got 5? Right here. Log base 5 of 2. Right? If you got a log and you want to evaluate, you got the base and the of, you can do change of base, right? Right? So you can do log of 2 divided by log of 5. Do common logs on it, right? Where? Down here? Here? Well, I rounded off to made it 0.4307, but really that's, if you keep the decimal of this, that comes out to be 5 exactly. But I'm thinking, okay. Look on the back of your sheet. It's property. Look at the 1, 2, 3, fourth one down on the back of this formula sheet. Look at it. What's it say? B log of B 2 equals, right? If this and that are equal, then X ought to be what, 5? Y'all see that? Properties of logarithms. This one right here. So if my x's, and here's my x's, right? Let me do my, here's my x's, and then here's my what? My b's, right? So it had to be what? 5. It's just a property, and it really ought not even be that.